Hello and welcome back to High Peak Education. I would like to perform an example problem where we are using rotational kinematics but also relating them back to linear kinematics. This will be a car during a panic stop, so the rotational kinematics will be observed about the tire. So let's read. During a panic stop, a car decelerates at 7.00 meters per second squared. The car's tires have a radius of 0.280 meters and had an initial velocity of 95 radians per second. A. What is the angular acceleration of the tires, assuming that they do not slip? B. How many revolutions do the tires make before the car stops? C. How long does it take to come to a stop? D. What distance does the car travel in that time? E. What is the car's initial velocity? Okay, so there's several parts to solving this problem. So in order to solve this problem, I believe we should probably write down our known values that are associated with rotational or linear variables. So let's start by saying during the panic stop, a car decelerates at 7.00 meters per second squared. So since the car is decelerating, we know it's linear acceleration. So it's linear, which is the same thing as its tangential acceleration, is, let's call it negative 7.00 meters per second squared, because the car is slowing down. The car's tires have a radius of 0.280 meters, so let us write that down. 0.280 meters, and then they also had an initial angular velocity of 95 radians per second. So that's omega initial is 95 radians per second. Okay, part A, we want to know the angular acceleration of the tires. Okay, so let's write each of these down sort of in shorthand form. In part A, we want to know alpha, that's the question mark. In part B, we want to know how many revolutions the tires make. So I think we need to find delta theta, but then we need to make sure that that is then put into units of revolutions. Okay, C, how long does it take for the car to come to a stop? So I think that's the time that elapses. D, what distance does the car travel during this time? So I think that's the variable delta x. So that's the horizontal displacement. Okay, and lastly, part E, what is the car's initial velocity? So what is v initial? All right, now that we have everything written down, we should be able to start looking at this problem first by figuring out the angular acceleration of the tires. So we have the tangential acceleration. So hopefully you recall that in the relationship between rotational variables and linear variables, along the outside linear edge, given a certain radius, we know that tangential acceleration should equal to angular acceleration times radius. So that is exactly what we have. And we should be able to solve for angular acceleration just by division. So tangential acceleration divided by radius is angular acceleration. And let's put the numbers in. So that's negative 7.00 meters per second squared divided by a radius of 0.280 meters. So let's get this alpha, and the calculator, negative 7 divided by 0.28. We don't need the significant digits in the calculator. We get exactly negative 25. And it's 3 significant digits, so let's write this as negative 25.0 meters per second squared. So this is our first answer. Part B, how many revolutions do the tires make when it comes to a stop? Well, we know the initial angular velocity was 95 radians per second. What should be the final angular velocity? Well, we're told that the car comes to a stop. Okay, so I think that the initial angular velocity was given, but the final angular velocity should be 0 radians per second, and then even the final linear velocity is 0 meters per second if you want that. So this is 0 radians per second. Then delta theta is the variable we're looking for. The time is unknown, but for now we can ignore it, and we found the alpha, negative 25.0 radians per second squared. I should put this as radians per second squared. Sorry about that. So this is angular acceleration. It should be radians per second squared. Okay, sorry about that. So now, the reason I wrote out initial, final velocity, displacement, time, and acceleration is because that should remind us of earlier in this course, we did linear kinematics and put the variables exactly in that order. We're ignoring the time, and we're ignoring the time to tell us which kinematic equation we should use. So the equation of kinematics for rotation that ignores time here for part B, that equation should be the following. So it should be omega final squared is omega initial squared plus 2 alpha multiplied by delta theta. Remember, delta theta is not 2 variables, it is just 1. So I think we want to find delta theta, so I think we have to subtract this initial velocity squared over. So that's omega final squared minus omega initial squared, and we need to divide by 2 alpha. So we have this expression, let's put the numbers in. So this should be omega final squared, which was 0 radians per second, and we square that, minus the initial angular velocity of 95 radians per second, and we have to square that. We divide this all by 2 times the angular acceleration of negative 25.0 radians per second squared. So now let's go back to the calculator. So we need, let's go alpha F1 for a stack, numerator over denominator. And let's perform negative, and it's going to be 95 squared. Now notice, by order of operations, this will give us a negative number because we're only squaring the 95 and then taking the opposite, that is the minus at the end, and then multiply downstairs by 2 times negative 25. So let's get our answer. Okay, so our answer as a decimal is 180.5. So this is delta theta equals 180.5 radians. Now we want to jump for joy as if we're already done, but we don't actually want radians, we want revolutions. So even though radians are SI units, revolutions are certainly more common out there in the real world. So let's get rid of radians and let's go to revolutions. And hopefully you recall that 1 revolution is 2 pi radians. So let's go back to the calculator and let's say 180.5, there's that number. And we need to divide that by parentheses. This is important. 2 times pi. I cannot tell you how many times I've dealt with students that divide by 2 pi without the parentheses, and the calculator takes half and then multiplies by pi. So just be careful with your order of operations there. So that should be 28.7 or so revolutions. 28.7 revolutions. Excellent. So that solves part B. Now on to part C. How long does it take to come to a stop? Now notice these kinematic variables. Previously we ignored t. So now we want to find t. But notice, now we can use any kinematic equation we want, except for the one that ignores t, which was this square of rotational velocities equation. So, as long as your delta theta is correct, you don't necessarily have to use the equation that ignores delta theta, but I would suggest the equation that ignores delta theta, which is the definition of acceleration, is probably the easiest. It has the smallest number of variables and they're most easily expressed, I should say. So omega final is omega initial plus alpha t. Remember, this is the definition of acceleration for rotation. So we want to solve that for, let's see, time. So, and the nice thing is this omega final is also 0. I'm happy for you to cancel out any variables that are 0 before even doing the algebra. So this should be minus omega initial equals alpha times t. So t is omega initial with a minus divided by alpha. So we should be able to put the numbers in. Minus omega initial is minus 95 radians per second. And then divide by alpha. So divide by negative 25.0 radians per second squared. So the calculator tells us that that's negative 95 divided by negative 25. So that's exactly 3.8. So 3.80 seconds when rounded to 3 significant digits. All right. This takes care of parts A through C. I'm going to go on to the next board in order for us to finish the problem and calculate parts D and E. Okay, now part D. What distance does the car travel in that time? Okay, so in order for you to hopefully understand this, I want to draw a picture that is a sketch that really communicates the idea. So I'll use my shapes and show on the side over here really what we're trying to say. So imagine the wheel is sketched like so, and the ground is sketched like so as well. And imagine that the wheel has, let's say, some double-sided sticky tape, which is also colored on the outside. You could also imagine that maybe it's painted on the outside and that the paint does not wear off. But you could imagine that as the tire is rotating during this panic stop, the number of times we go around the outside, however many revolutions that is, we calculated that on the last board, that each time there's a revolution, that the paint or the double-sided sticky tape that's colored on the outside of the tire lays itself out flat. So what we're really saying is the delta x, that is the distance that the car travels, this entire time it's undergoing the panic stop, is equal to the total circumference gone around by the many times of the car being revolved. Now, by the way, what that effectively is going to mean is we need the total arc length, that is the total rotational distance around that the car goes. So we can solve part D by saying S, which is the distance around, is equal to delta theta times R. Now notice, if delta theta is in radians and R is in meters, we can just get S in meters. So S, and by the way, S, we just talked about that the total S should equal to this delta X. So it's really the same thing. So delta theta in radians from the previous board, we saw that to be 180.5 radians. So we need 180.5 radians. And we multiply that by the radius of 0.280 meters. So let's go ahead and calculate that. So we need 180.5 multiplied by 0.280. So we get 50.54 meters. Let's round that to 50.5 meters because of the uncertainty with the significant digits. Now, by the way, previously students have asked me, what about if you tried to do this using revolutions? Well, you could, but think about this. Either the distance around is the radians times meters to give meters. In other words, it's the unitless radians times the unitless meters. Or you could have calculated this S or delta X as the delta theta in revolutions times the distance it takes for one revolution, which would be capital C, and where capital C is defined as 2 pi r. That's the circumference. So if you want to use revolutions, that's fine, but you have to get this in circumference, because the circumference is just one revolution. By the way, this simplifies to this if you change revolutions to radians. Okay? So, it gives the same answer. Lastly, part E. Part E says, what is the car's initial velocity? That's actually an easy question, because V initial is equal to omega initial times r. So that's linear velocity related to angular velocity. So this is 95 radians per second multiplied by the radius of 0.280 meters. So let's get this number. So 95 radians per second multiplied by 0.280 should be 26.6 meters per second. 26.6 meters per second. Now, by the way, whenever you perform an analysis like this, you should ask yourself if this seems to make sense. So, an alpha of negative 25 radians per second squared doesn't seem extremely large, but it seems reasonable. We note that in part B, 28.7 revolutions, about 29 at times around, that seems relatively reasonable. And the car takes 3.80 seconds. So we've all seen cars stop from high speeds, and just under 4 seconds seems like a reasonable possible time. In fact, we know now that the car was moving 26.6 meters per second. So a little bit more than doubling gives the velocity in miles per hour. So we're probably talking close to 60 miles per hour or so. And again, that seems reasonable, and the distance is 50.5 meters. So that's going to be a little bit more than 3 times for feet. So we're talking, let's see, what is that? 155, 160 or so feet. Okay, so this seems reasonable for a panic stop. So we believe we have the correct answer. Thank you very much for watching High Peak Education. Please smash that like button if you enjoy this content. Please subscribe to the channel to grow the channel. Please share this amongst your social network. And I look forward to also seeing your comments. I will see you in the next video.